wide field, and I decide to, I picked some topics out where I thought it could be helpful for you, but in the beginning, uh, you you should choose the use the choice to ask things, and when they are not covered in my lecture, I will try to answer them directly. So is there some topic which stress you all the time in your working life and you don't know what it is? One name, one measurement, one terminology. Okay. If there's some, please interrupt me or ask me. Um, let's start with a little warm-up exercise. When you enter a car and you see that in front of you, um, what tells us this measurement about the car and things we can do?
What do you mean? Like how many kilometers per hour?
Yeah, what came in your mind when you see this in front of you?
Mm,
Like the fastest it could possibly go if it was going at full power. Yeah, over a certain amount of time, but in general, just when you have your foot down.
Fuel level.
Yeah, as well the fuel level. So how long you can drive, and maybe how long you can drive with full power, things like that. But the main thing is you should be aware is that you have the possibility to go 220 kilometers per hour if you want to, but you don't have to. And normally you wouldn't. Most time, if you are driving in the city, you will drive between 20 and 50, something like that. And sometimes you will, when the street is free, you can go faster. So what tells us a nominal capacity of 2 megawatts of a windmill?
3 megawatts is the maximum capacity that the windmill can produce.
Exactly. And normally it didn't or don't want to produce 3 megawatt just when there's a lot of wind. So normally it's like you in the city, the mill will produce something between 0 and 3 megawatts. And this is very important. So the 3 megawatts or 10 gigawatts of something didn't tell you the amount of or how many kilometers you will drive or how many energy you will earn. It's just says you in ideal conditions, the maximum power of this plant is 3 megawatts and never more. So this is it sounds simple, but it's very important. It's for a lot of people very difficult to understand what this 3 megawatts mean. So just to get an idea how much 3 megawatts are, 3 megawatts are a standard windmill of today, but there are already some with 10 megawatts. These are the biggest at the moment. An offshore wind park might have 1 gigawatt, so this is 1,000 times, 3 zeros more than a megawatt. And this is more or less the same like a standard nuclear power plant. Our brain, if it works, if we are not sleeping, or maybe even when we're sleeping and dream interesting dreams, produces 20 watts. So this is yeah, a lot of zeros less, or it's behind the zero, or no, it's a lot of zeros less than the megawatts. A normally doped cyclist produces 400 watt. Sometimes in the mountains up to, yeah, might be 600 watt, but this is really not much. And these are only athletic people. A normal human is able to yeah, produce 100 watt during his working day. So there could be peaks, but normally not more than 100 watt. Your washing machine needs between 2 and 3.5 kilowatts. This is 3 zeros more than watts. So yeah, this is a lot of work you don't have to do. And 3.5 is this is dependent on the how you call it, Sicherung,
The fuse.
the fuse, yeah, of a normal household. This is normally a limited limit things you can connect to the grid to 3.5 kilowatt. A horse is able to, if it's really run very fast, to produce 15 kilowatts. So this is this. I was very impressed of the difference between a human and a horse. So a horse has a lot more power than a human. The normal, the ECE 3 crane in Germany needs normally or is able to use 8 megawatts. So this is a lot more than a horse. So always between kilo, mega, and giga, there are 3 zeros more. And a star rocket during the start needs 43 gigawatts. So 43 times the energy production of a nuclear power plant. This is a huge amount of energy. And what the sun produces, I was not able to write it down because we need 26 zeros to describe this number. So this is really a huge amount, and there in the space there are some things like the melting of 2 black holes, which are even much higher. So just yeah, to get a little bit a feeling where we're talking about.
One question, Holger.
Yeah.
You have there like one small wind farm is 1 gigawatt and it's equal to the capacity of what is that, like a nuclear plant?
It's a nuclear power plant. This is not a small. This is an offshore wind farm.
And it's not a small one.
No, it's a normal. What they build today. Yeah. So it's yeah.
I have a question too. How much time then is this like over a day or?
This is why we start with this picture. This is exactly the problem people have normally. So these numbers didn't tell us anything about the time. They just tell us how much could be produced or used maximal. So these are very, very different things. And this is the main difference between, for example, the offshore wind farm and the nuclear power plant. So the nuclear power plant normally runs 300, let's say 50 days. The rest they need for a revision and replacement of the Brennstäbe. I don't know the English word. and how much the offshore wind park produces depends directly from the area where it's built. So if you have a area like in the northern of UK, where you have a lot of wind, a lot of hours with a lot of wind, will produce nearly the same amount of energy like the nuclear plant. If it's in the east, in the Baltic Sea, where you have less winds, or the wind is not so strong and not so many days of full speed wind, it's much less than the nuclear power plant. So as you see, the time is its important value, and this is the difference between power and capacity, or we'll see that later on. Here we have an overview about energy sources. This is a little bit mixed up. So the uranium, petroleum, natural gas are reserves, which are known at the time this picture was made. And wind is estimation about the wind, the amount of energy we could suck out of wind during a year. And the solar radiation, it's as well what we could earn over a year on the if the surface of or if we could earn all the radiation which comes to the Earth. And you see the brown button. This is the energy consumption over a year. It's today it's maybe a little bit higher, but this is to get a feeling about what can we do with solar and wind, and how big are the reserves of conventional energy sources. I like this picture very much. Yeah.
Could I ask you, so this is the reserves or of all time, or is it estimated? I didn't understand that.
These are the reserves we know at the moment. So we don't know much about the underground when it's deeper than 5 meters or 10 meters. So you have to dig a hole and to see what's down there. So we don't know exactly how much natural gas it's left in the surface of the Earth, and petroleum as well. These are the amounts which had been known or estimated at the time the picture was published. So this is all we have. If it's exhausted, there's nothing left. And you can try to put the brown button of the energy consumption over a year into the blue, or the gas button, or the petroleum button, or the uranium button, or coal, to see how long we could leave with the energy we have. This is not, I think it's not exactly it's a little bit, there's a little bit more than you could see it on that picture, because I think the diameter of the 16 terawatt hours didn't fit to the diameter of the others, but it's just to get an idea. So we have reserves for, I think, maximal 200 years if we don't switch the source of energy we use.
Excuse me, sorry for asking, but how many years?
I think between 200 and yeah, 250, something like that. So it really depends if you start to use oil sands and things like that, maybe a little bit more, but yeah, some 100 years. So I think the message is clear. Natural energy sources or reserves are will have an end within the next centuries if we didn't switch to something else. Okay, so the efficiency. If we have to, this is directly connected to your question. It also depends how efficient we will use the energy which is stored in fossil fuels. So normally you have a lot of losses. So there's a difference between the energy you put into a conversion system and the energy you could use in the end. We will have a deeper look to that later on. And the difference is named primer energy and end energy. So the primer energy demand is of course much higher than the end energy, which could be used. And this is a big difference between fossil fuels and renewables, because renewables produce directly end energy more or less. There's some losses, but there's not this conversion, this big conversion losses we see if we use fossil energy. Other phenomenon is there are losses we want to have. These are the losses, especially the heat losses of the Earth. So the Earth as a system gets a lot of primer energy from the sun. A little bit is converted into biomass, and a little bit is stored in the atmosphere, and a lot of the energy will be reflected to the space again. So, and this is where the climate efficient gases enter the game. So what they do is they are able to absorb or reflect heat radiation. So the heat couldn't leave the Earth anymore, and that's why it's getting hotter and hotter. Just to get an idea on that. So we have very different forms of energy. So we have at least in German, we call it internal energy. It's what we have in nuclear energy, where or atoms getting smaller and produce or lose energy with that. We have chemical energy. It's what you have in in the battery of the car or in batteries normally, but there are different types of chemical energy. What we use in our body is as well chemical energy. So we convert food to chemical energy, which helps us to move and to think and to be. And then we have thermal energy, which is in the end the movement of atoms yeah, what's most easy to understand is mechanical energy. So we have kinetic energy. This is when we speed up. Within the speed, there's energy, and we will lose this energy when we crash against a wall. So that's the moment where you get the best feeling of kinetic energy. And with potential energy, this is just if we yeah, take a weight and put it into the air, it is able to drop down again. This is potential energy. Or if you climb up a mountain with your bike, and you could use the potential energy to drive down the hill. Then we have energy in form of radiation. So this is solar beams and heat, not thermal heat. This is the heat radiation. And of course, we have electrical energy, where we think most about. Yeah, the symbols are not so important, but what is important to know is that there are a lot of different terms to describe energy, or the amount of energy. So nearly every every science, or every sector uses his own units to describe energy. So, in fruit, this is calories. We calculate with calories. The coil guys calculating with coil equivalent, or oil equivalents, or but this describes always the same. It's energy, and we use normally in the electrical area watt or kilowatt hours. And you can convert one unit into the other very easily. It's just multiplication with another number. To get a better idea of the energy we need, this is an overview, an average consumption of a person or a household in Germany. So you see, one person needs normally 1.6 kilowatt hours per year. You can have a look in your power bill to see if you are energy saver or energy waster. If you have electrical heat or water heater driven by electricity, it's much higher. So you will see the everyday shower consumes a huge amount of energy. If it's nevertheless, if it's produced by electricity or by combustion. Normally, you calculate with a four-person household. So this is in this table very easy. It's directly 4,000 kilowatt hours. Modern data center, I have to look it up. I saw this number just once. This could be much higher, but just to get an idea, that's why it's in red. Calculates the amount of 10,000 four-person households. So the playing around with your mobile consumes a lot of energy, not in your mobile, in all the backbone behind. And this is why digitalization is a driver for higher energy consumption. even if the data center getting more and more efficient, we really consume, or the amount of energy needed for the digitalization, it rises yeah, year by year. And which the numbers we see today, or we know now, it's very easy to calculate how much households you can deliver with energy by a 3 megawatt windmill. What you need to know is how many hours a windmill runs normally or average at full power. So this is the full load hours. Maybe some of you hear this word already. This describes or this is an addition of all the energy produced. So to come back to the car, you add or you put all the times together where you drive 20 kilometers and 50 kilometers and 60 and so on, and divide it to the hours you use the car, and then you know the average velocity you have have driven in the last year, and this is and then you can or what you can, or no it's you put all the velocities and the time where you drive 20, 40, 60 kilometers per hour together, and then you divide it to the maximal speed, and with that you know how much time you have used maximum speed. I think it's a little bit complicated, but in the end, it shows us the hours a wind or the amount of energy the windmill had produced. Maybe I should produce an extra slide for that. So you just multiplicate 3,000 kilowatt, which is the same as 3 megawatts, with the time the windmill runs average at full power. So 2,150 is the number for a modern German onshore windmill. Of course, you have some locations where you have higher full load hours, and a lot of locations where you have less full load hours. So this is an average again. And then you see, okay, a windmill produces an average onshore windmill in Germany 3 megawatt onshore windmill in Germany produces an average amount of 6,550,000 kilowatt hours per year, and this is sufficient to deliver 1,000. I could see my slide because 1,000 600 something for person 12 it was for person households with energy.
But like I have one question here. Like you said, like so one, like there's a lot of calculations, but one like windmill will be able to deliver, has a capacity to deliver in full power a small city of about 6,000 people, right? Because if it's 1,600 households of 4 people, then it's about 6,000 people.
Yeah.
That's the kind of the summary.
Yeah. Yeah.
Okay.
This is a big windmill, a modern windmill, and yeah, depends directly on the location and how many hours you have wind and how strong the wind blows. But yeah, to get an idea. Other questions? Thoughts? What we saw in the last slide was the energy consumption of a household, but the electrical energy consumption of a household. And we didn't take into account hot water production. But the electrical energy consumption is not the whole energy consumption of a household. There's a lot more we need. And what you see, this is in German, but the yellow part of the column, it's the energy we need to heat up our flats. So what you see is that the biggest part of the energy consumption of a household is heat, not electricity. So when we want to reach 100% renewable energy system, we have to replace the heat, which is normally done by gas or coal or things like that, with electricity. And you see, this is a really big part of the cake. And you see the heat consumption between 2008 and 2018 goes down. I have to see if it's not set exactly for what. But what you can see in the next slide, which is in German again, is the most interesting part is the gray line on the top, which shows how many square meter a person in Germany uses for living, or how big the flat is. And you see the energy need per square meter goes down, but the square meters per person rising. So all the efficiency measures we gain by Dämmung, isolation, are feed up by the amount of space we use. And of course, you need more energy to heat up a 8 square meter flat than a 80 square meter flat than a 60 square meter flat. So the size of your flat is directly connected to the energy, or to the energy need for heating, and this rises. So this is a problem within the system. Just to have an idea. Here we are back to this primer energy and energy diagram. This is the energy efficiency of a light bulb. So on the left, you see the primer energy contained in coil. You put into the coil power plant. Then you see the big red arrow. These are the losses. It's normally heat. And you see the amount of electricity produced by the power plant. Then you will have some losses in the transmission lines and the distribution lines. and in the wiring of your house. And then where the next thick red arrow arises, we are entering the light bulb. This is a conventional, and you see that the biggest amount of the energy which enters the light bulb will be emitted as heat, and a very, very small amount of the energy entering the light bulb will be emitted as usable light. Then you have some losses by lampshade and things like that, and in the end it's just 1% of the energy you put into the system which you earn as light in your house. So this is why the EU put in elaborated this regulation to kick out conventional light bulbs, and we now using more and more LED lamps or energy efficient lamps, which have a much higher efficiency than the conventional lights. Here you can see the gains and losses of a heat pump. So we have again a lot of wasted heat within the power plant. If we drive the heat pump with a power plant, we don't have these losses if we use renewable energies. Then we will have some transmission losses and the amount of energy entering the heat pump. This is VP. It's German Wärmepumpe, but yeah, you should imagine HP. And what the heat pump does is it takes a lot of ambient heat from the air around or from the ground, and add this energy to the electrical energy, so that you generate in the end much more energy in form of heat than you put in form of electricity. So this is why electric heat pump is very efficient. It's even more efficient if you use renewable energy. Here you have an overview. This is in German again, sorry for that, about different heating systems. And you can see if you have an isolated old house with a gas a gas oven with a gas heating system, and you use power to gas in between. So what some people want us to sell, to produce a huge amount of hydrogen or to make power to gas out of it, you need a lot of energy in form of power, and then you convert it to gas, and then you convert the gas to heat, and this will need a huge amount of energy. It's the double you have if you use gas directly. You don't have the CO2 emissions in the first way, but the energy you need, it's the double than the energy you use by a gas heating system. If you have a CHP unit in between, so if you produce heat and electricity at the same time with the gas you consume, and the production, 40% of the energy is converted into electricity, and you feed it back, it's even less efficient than the direct use of gas. If you use a heat pump with a it's called annual efficiency number of 2. So this is more or less a air heat pump, which is not really optimized. You will need this is a gas-driven heat pump. Sorry, if you use a gas-driven heat pump, so you can drive a heat pump by gas or by electricity, and if you use gas and you have a efficiency number of 2, you are much better than, or it's nearly half of the, or it's a half of the energy you need by direct gas firing. If you use an electrical heat pump and renewables, you will come down, yeah, more or less the half of the energy. And if you use a ground or ground or ambient or surface, or how you call it, earth heat pump with a very high efficiency number, you can reduce your energy consumption dramatically down to 3,000 kilowatt hours in a year. So this is why heat pump is a really the solution number 1 to produce heat for your home. Here we see the efficiency of cars. So if you use a normal car with fossil fuels, you will drive 1.5 kilometers with 1 kilowatt hour energy. If you use synthetic fuels, so if you convert even renewable energy to hydrogen or to power to liquid and use that in your car by combustion, you will be less efficient than by using fossil fuels. If you use a fuel cell, you are a little bit more efficient, so you can drive 2 kilometers by 1 kilowatt hour primer energy. And if you drive 100% electrical, you are much more efficient than all the other solutions. You can drive 5 kilometers per kilowatt hour primer energy. If it's 100% renewable energy. If you use conventional energy, you have all these losses, this efficiency losses in the conversion of coal to electricity we saw in the beginning. Yeah, questions up to now? Other things you want to know? Otherwise, you will have to leave the comfort area, and we will enter more physical things and try to understand electricity. How many minutes we have left? I couldn't see my watch at the moment.
15 minutes.
15 minutes? Okay. So let's try to enter that field. The most important thing to understand electricity in the way we use it day by day is to get an idea, of what are waves. This is the typical wave of a AC current, and you can see the period. This is the frequency. So how much time is needed to have all the cycle of the wave. Then you have the peak, which is the voltage. So If we have a 220 volt, we have, yeah, the peak is 220 or 250 or 40 we have at the moment. And there, yeah, these are both things which are important. And this wave dominates more or less our whole life, even if we don't know it. We have waves all around us. So if you see something, what you see is the wave of a specific length. This is the colored part of the graph. We have on the left side very short waves, so with a very high frequency. There we are entering the radioactive radiation and space radiation. Directly after the visible spectrum, we're entering infrared, which is heat, or we feel as heat. And then, yeah, we're entering the radio frequency, and after that, we're entering the area of electrical energy we use, and on the right of that, we're entering what you hear at the moment, sound waves. So all this is based on electrical or electric mechanical waves. Without them, you couldn't see, you couldn't hear, you couldn't sweat, nothing. What a generator does is, or a power plant does is, it uses magnetical fields to produce electricity. I don't expect that we're entering these slides today, so yeah, maybe I have to produce some more. And you see there are three different waves together, which is normally the form we transport power into the transmission lines, distribution lines, and just in the household we just use one of these waves. But if you have a electrical water heater, it will also use all three waves. And you see this very big machines we will need to do that in the power plants, and we come to that later on. So the frequencies for of the current is not only depending on the power plant itself, it also depends on the consumption. If a power plant runs without consumption, it will run faster and faster and faster and faster, because it's very easy to run. This is yeah, like you would be driving a bicycle without any friction. You would be able to go faster and faster and faster. If the consumption is in balance with the production, we have in Europe at least a frequency of 50 hertz. And if the consumption rises, it's you need more energy, or yeah, it's like a hill on your bicycle. You need more energy, so you're getting slower. And this is what happens if the consumption is not in balance with the production. The frequency of the system goes down step by step. So this is this is the main the main work of the transmission system operators to keep this balance always in line, more or less. If they are not able to do that, we will see that. So on the left side, this is a blackout we had in Italy, 2003. And you see on the left side, the frequency was at 50 hertz, like it should be. And then there was an outage, and the frequency begins to escalate. And then it drops dramatically, and the European grid was separated in 4 parts automatically to save the other areas. And then they start the automatic pumping, so they start to activate fast reserves to stabilize the energy. But they lose a millisecond later a very big power plant. This you should keep in mind. We will have a look why this happens. And then the frequency goes more and more down, and other power plants switching off. And in the end, there was a blackout. So no energy anymore in the Italian grid. And all of this takes place in 2.5 minutes. So it's very fast, not many time to react. Why this happens? This is, there we come back to what I said a slide before. If this big generator needs more and more energy to turn, or if the mountain you want to drive up is your cycle getting steeper and steeper, you get more and more friction on the wheel between the generator and the turbine. This is on your bike would be the chain, which is in danger to crack. And this is why the power plants have to switch out at the specific frequency. So it's really the danger that this whole machine breaks because it's so there's so many power needed to turn the generator, and that's why here in the this big power plant switches off, because they're very in danger to get damaged. And then the others followed very closely because they are coming into the same danger. So in a 100% renewable world, we don't have these problems. We are with a renewable power plant and the converter, we are able to keep on running with other frequencies. In the end, there's not really a limit. The limit we have at the moment is artificial to be adaptable to the existing power system. But this is the frequency is mostly a problem for the very big power plants. But it's a serious problem. This could cause blackouts. So now we are entering the auxiliary services. I was not able to translate it fully at the moment, but how many minutes we have left?
3 or 4.
Yeah, so maybe we keep that for another time. And I stop here and give you again possibility to ask questions.
I have a question.
Yeah, great.
So you just said that the limit that we have set is artificial, but with renewables, I didn't quite understand. So if we have renewables, it can be a higher frequency.
Yeah, we some islands, in islands you normally you don't have such a stable frequency because you just have one generator and a lot of consumers. And in islands, the frequency is or the safe frequency it's higher, so there are variations of some hertz are allowed, and renewables could do that very easily. So they have a converter. They're not directly connected to the grid, and they can deliver each frequency you want to. Of course, the consumers also have to be able to deal with different frequencies. What normally happens is your washing machine goes a little bit slower, and the heat production is a little bit lower if the frequency drops, but this is not really a problem. And yeah, in islands, they mostly use CHP or small generators, which are specially adapted to deal with bigger frequency variations. So what they do is just to make the wheel more stable, and yeah, there we go. Other questions? You are.
So for the devices on the other end,
Yeah.
What is risky is not a change in frequency, but a change in voltage.
Yes, of course there are some devices which needs the frequency, especially in nano or micro layer productions or things like that. They really need a stable frequency, but they normally have their own devices to guarantee that. And nowadays we see more and more loads which are connected as well over converters to the grid. So in the past there were some big pumps and some very big machines which have been connected directly to the grid, and they will getting more fast, which could be dangerous. But nowadays we see less and less of this machine. So the load side normally didn't has these problems. And so that the blackout was not caused by the load side, it was caused by the power plants itself.
Okay, any more questions? The time is 11, but do we have any more last questions for Holger?
Could I ask one last thing about the?
Yeah, of course.
So 50 hertz, is it? Why was it set at 50? And like, does it have with the? Does it make any sense why it's 50?
Not really, because 50 hertz is a frequency which is especially dangerous for human beings, because our heart has a similar frequency. United States use 60 hertz. So there are other systems with other frequencies, and the train system use 16 hertz. This was goes back to the really first moments of electricity or when electricity comes up, and yeah, there's there's no deeper reasons to choose one or the other frequency. Okay, then a lot of fun in verdauen, digesting, yeah, and we will see us next week with gas topics.
Yes.
Okay.
Thank you so much, Holger.
Danke.
Ciao.
Bye.